Dear students, today we will discuss about the types of statistics. Different physical situations encountered in nature are described by three types of statistics. First is called the Maxwell-Boltzmann statistics. This statistics is also called as MB statistics. Second is called Bose-Einstein statistics or BE statistics. Third one is called Fermi-Dirac statistics or FD statistics. Okay, these are basically the three nomenclatures for the MB, BE and FD. We will also discuss these statistics in detail, but first we will see their background. What are these all about? Okay, this first, that means the Maxwell-Boltzmann statistics. This is also called as classical statistics because it was basically developed long before the advent of quantum mechanics. The Bose-Einstein and the Fermi-Dirac statistics, basically these are collectively called quantum statistics. That means you can classify these two also into classical statistics, which includes MB, and quantum, which includes B and FD. First, we will look at MB statistics, that means Maxwell-Boltzmann statistics. In this, particles are basically assumed to be distinguishable. This is very, very important. That means they are distinguished from one another, distinguishable, and any number of particles may occupy the same energy level. If you have different energy levels, E0, E1, E2, so here in this MB statistics, this any number of particles may occupy the same. This is very important. First is any number and second is same energy level. So what are the particles which basically obey this Maxwell-Boltzmann statistics? Those are called as Boltzons or Maxwellians. These particles are basically spinless, or you can say zero spin. Zero spin or spinless particles, those are called as Boltzons or Maxwellians. Why? Because they obey this Maxwell-Boltzmann statistics. Okay. Now, the second one is called as BE statistics. Here, particles are indistinguishable. In the first statistics, we discussed the particles are distinguishable. Here, indistinguishable, and also any number of particles may occupy a given energy level. This type of statistics is basically obeyed by particles having integral spin. For example, hydrogen molecule, deuterium, nitrogen molecule, helium, but helium 4, and photons. Very important. That means photons are basically These are also called as bosons. That means particles, these type of particles which have this integral spin and obeying this type of statistics, those are simply called as bosons. Okay, that means bosons are simply having the integral spin 1, 2, 3, 4, 5, 1s, 2s, and so on. Okay, next and the last one is called Fermi Dirac statistics, or this is also called as FD statistics. Here also particles are indistinguishable, but the difference from above statistics is only one. Here it is very important, only one particle may occupy a given energy level. This type of statistics is basically obeyed by the particles having half integral spin, or you can say odd half integral spin. For example, 1 into 1 by 2. First, they should have half integral spin, but it should be odd. Okay, 1 into 1 by 2, 3 into 1 by 2, and 5 into 1 by 2. So it is very simple. That means this type of statistics is basically obeyed by the particle is having half integral spin. Okay. For example, protons, electrons, helium-3, nitric oxide, NO are the examples for Fermi Dirac statistics. And the particles which obey this type of statistics are called fermions. So fermions are particles having half integral spin. Similarly, bosons are particles having integral spin, which you have learned in the previous classes also. But remember this time here, these are very important, these terms. Okay. In the advanced studies or courses, you will study fermions are basically those species whose wave functions are anti-symmetric with respect to the exchange of particles. This you will see in the quantum mechanics further. And bosons are those species whose wave functions are symmetric with respect to the exchange of particles. Here, if you want to remember this thing, please remember. Otherwise, for this course, this is very important. What are fermions, what are bosons, and what are bosons. Okay, and which type of statistics they basically obey. Now, another important topic is called Stirling's formula, or this is also called Stirling's approximation. Stirling formula or approximation. You know, natural logarithm of n factorial is basically equal to n ln of n minus n. But a better approximation was also given, which includes that ln of n factorial is equal to this term n ln of n minus n plus ln of square root of 2 pi n. You can write this way, under root of 2 pi n or 2 pi n whole power half. Okay. So this is better approximation than this one. We will see by taking different examples also why this is better example. So you have to remember that as the value of the n increases, a number of entities or molecules increases, very small gap lies between Stirling's approximation, and this is called beta approximation or second approximation. This was first approximation which we use. This is simply called Stirling approximation. This one is called second approximation, and it is a better approximation. Why? We will see by taking different examples. For example, you are supposed to calculate ln of 10 factorial. ln of 10 factorial. You will simply write 10 natural logarithm of 10 minus 10. You know natural logarithm of is basically equal to 2.303 of log. So in place of natural logarithm, you will simply put the value 2.303 into log, and this is the quantity, and here so you will introduce the value 10, 10, and you know log 10 is basically equal to 1. This term will be equal to 1. Log 10 is 1, so when you multiply 2.303 by 10, it will be this much, and subtract minus 10, and this will be 13.03. We have basically calculated from the using the Stirling approximation. So first remember this answer that it is 13.03. Now we will use a better approximation here. What is better approximation? Better approximation is basically ln n factorial is equal to n ln n minus n plus ln of square root of 2 pi n. Okay. When we put the values here, you can use a calculator, scientific calculator or simple one. It is very easy here. 10 ln of 10, you can do the same procedure for this. It will be 2.303 log of 10, and multiply this minus 10, it will come out to be 13 point, plus you will add this term. First calculate this and take square root, and then take the natural logarithm of this. You can take it directly from using the scientific calculator. Okay, so it comes out to be 15.10. So we have taken ln of 10 for both the cases, for this case and this case, and because this was also equal to n was also equal to 10. So what is basically the difference, that why second one is called a better approximation? You will see it by this example here. If we want to calculate the relative error between the two, it comes out to be 15.10 minus 13.03 upon 15.10, and is equal to 13% error. Please also do this manually at home using a calculator. Now here n was simply, remember also, n was very small. That means the number of entities were small, very small. That means almost 10. Now that means, now suppose if we want to calculate it for higher numbers, n is very very large, suppose of the order of 100, we will first use the first approximation and then second approximation respectively. So ln of 100 factorial will be equal to n ln of n minus n. So it will turn out to be 2.303 log of 100, can also be written as log 10 raised power 2. It is n log n. So this comes here, it will be multiplied, and log 10 will be 1. So you can calculate it very easily. It comes out to be 360.6. Now we will use the second formula of the Stirling approximation, that is ln of 100 factorial will be equal to 100 ln of 100 minus 100 plus ln of 2 pi 100 under root. This comes out to be 363.62. So relative error will be 363.62 minus 360.6 upon this much. It comes out to be 0.83%. That means as the n value of n increases, the first approximation and the second approximation gave almost the same values. That means their relative error is very very small as the n number n entities go on increasing, or n is very very large. So at home you can do a very simple exercise. Suppose take make a table n factorial, another column. Suppose this is n factorial, then ln of, then take natural logarithm of ln of n factorial, then make this Stirling approximation n ln of n minus n, then calculate the relative error by calculating with both these formulas, first Stirling's approximation and the better approximation, then calculate. For example, n first 10 and 100 we have calculated for example now 1000 here, or you can also do it for 2000 or then 3000. Okay, you have to take n this much and do the same procedures by using both the formulas and calculate this type of error. This is also asked in many exams, particularly in the CSIR. This is sometimes asked, so this is very important. You have to make a better approximation, and they will tell you which one is the better approximation, or what is the relative error between the two. So you can do this by following this table. You can do a simple exercise on this. Okay, now there is one more thing regarding the Stirling approximation, that is it is proof. Okay. First, suppose you are given n factorial. This can also written as n, so this is n multiplied by n minus 1, n minus 2, n minus 3. That means factorial. Suppose you are being given 8 factorial. How you write it? You will first write the n, that means 8. Okay, then multiply it by 7, which is basically equal to 8 minus 1. Okay, then you write the second one, that means the 8 minus 2, and so on up to when it comes out to be 3 to 1. You can directly write it as, suppose 8 factorial is equal to 8 multiplied by what you have learned in the mathematics also, 8 into 7 into 6 into 5 into 4 into 3 into 2 and into 1. That is, I can make this model in terms of this. Suppose I have now the n factorial, it will be n minus 1, similarly n minus 2, n minus 3. Here I am taking 8 as n minus 1 will be 8 minus 1, that will be 7, like this one, and so on, and it comes out to be this. So you can take this side also, that n factorial is equal to 1, 2, 3, and so on up to n minus 2, n minus 2, up to n. The number which you have started from. Suppose I started from 8 factorial, here it will come out to be 8, here it will come out to be 1. So now you can do the practice at home for this very simple question. So suppose now n factorial is given. This can please make a correction here. It is n factorial. Always remember this is n factorial. Suppose if I take 4 factorial or 3 factorial case, it will be first n multiplied by something. Okay. Now suppose this n factorial is equal to 1, 2, 3, n minus 2, n minus 1, and n. Now I am taking the natural logarithm on both sides. You know, multiply will change into this plus m into n into plus. Okay, so it will be ln of n factorial, this one, and similarly it will be ln of 1 ln of 2, ln of 3, ln of 4, ln of 5, ln of 6, ln of so up to ln of n. Like if it was 8, so it was ln of 1, 2, 3, 4, 5, 6, 7 up to ln of 8. That means here it is ln of n. Last you will see here it is ln of n. So you can also write this term into ln of n is basically equal to summation n runs from 1 to n total n ln of n small n. This is small n 1 2 3. So you should also remember that ln of 1 is basically equal to 0. That means you are basically adding or making a summation of these terms. First, I will show you a simple graph here. What does this mean? Suppose if you want to calculate, if graph is given here, yes, please concentrate on this graph first. Suppose this is y-axis, it contains, this is y in terms of natural logarithm. ln of 1 is basically equal to 0. You know ln of 1 will be 0, so I will write it as 0 to ln of 3, ln of 4, ln of 5, ln of 6 is up to suppose ln of n, up to ln of n fact n, here ln of n dash dash. So I can make the different segments based on my number. So here it is the total number of n given. This x-axis, suppose 1 2 3 4 5 6 suppose. Now I want to make a sum between the two. It will be, suppose here this will be ln of 1 is 0, so it will be 0 into 1 will be 0. So that is why this here it will be no curve at all. That means it will be on the same x-axis. Okay, now ln of 2 multiplied by this one, it will be equal to ln of 2 again, so its area will be this much. Similarly, ln of 3 multiplied by again this one unit, it will be this much area under this bar. Similarly, ln of 3, ln of 4, and dash 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 up to ln of, suppose ln of n. Now I have to actually make a summation. I have to add the areas of these bars. Okay, area under these bars. But what is the better approximation? It is general approximation. I am making y with respect to n. This is of this formula, y is equal to ln of n. Okay, this is the function. But if I want to make a better approximation, what we do in integration, we basically integrate this curve. That means I will take these values now, this curve value, these curve values, these are the ln of n values, these values. Okay, I will exclude these ones but take the approximate value, this one. This will be a smooth curve. I'm making many curves here, but this will be a smooth curve, so it will be y is equal to ln of n type of curve. So going back to the part what we were discussing, that this one, that means this ln of n is basically summation. Suppose ln of 1, that means that bar was equal to 0, its area was equal to 0, and similarly ln of 2, ln of 3, they have particular areas under those curves. Okay, so now we are taking a situation when this n is very large. Here n becomes very large. The difference between its successive values becomes very very small compared to the values of n. That is that smooth line. Otherwise, if I want to make small n values, then there will be difference between the two. But if I have greater number of n values, they will come close to each other. Like in integration, what we do, they will come close to each other and they give us a good value here. So So basically, when this n, that means the number of molecules or entities become very large, the difference between its successive values becomes very small compared to the values of n. Therefore, this summation here, summation of terms on right hand side of equation, this one can be replaced by simply integration. Okay, so I can write ln of n factorial is approximately equal to ln of, this is small n, here it is capital N, that means total number of molecules, here are total number of entities, and dn integral from 1 to n, integration of ln n dn 1 to n. Okay, that means I have replaced this summation by the integration. Okay, first you have to make this point clear, because when the point has become very close, I can take the now the values under this curve. That means if I want to calculate the area under this curve, now only under this curve only, it will be integration, you know this one, from integration. So this will be the integral of this ln of n dn. Okay, now what we do here, suppose ln of is approximately equal to ln of n dn. We have to integrate from 1 to, here not 0, it is 1, 1 to, and last value we have upper value, higher value, that is capital N, that is why this is 1 to n. So simple integration by parts will be used here, which is integral of, here integral of u dv, you know this integration by parts, u dv will be equal to uv minus integral of v du. Okay, this is integration by parts. You can see this formula and use here. How to use it? We will first split this term. Suppose it is multiplied by 1. ln of, this is small n. Remember here, this is small n here. This is small n. Small ln of n, it will be u, and 1 will be v, and this is dn. Okay, making other approximations, we can take uv ln, then v becomes n, ln of n, v minus, then we have v du. That means if we differentiate, because du will be here now equal to d ln n, that becomes 1 upon n into then dn. So we will integrate it from, that means we have lower limit 1, upper limit n. So we can write it is actually multiplied by this n. Now you can write into this form, n ln of n. This is natural logarithm of n multiplied by n, or you can write it n ln of n. So this n and n will go here, it will remain the integral of dn only, and we have upper limit and lower limit 1. We will make the upper limit and lower limit, so integral of differentiation of n will be equal to simply n, so it will be minus n. We will first give the upper limit minus lower limit. So upper limit here, this small n will be replaced by capital N, that means capital N ln of n minus n, then again minus. Now we will introduce the lower limit, that means in place of 1 we have to take 1, n 1 ln 1 minus 1, it would have been minus 1, but it is already, minus is outside, we will take minus to here, and it will be plus 1 there. Okay, so you remember ln of 1 is equal to 0, what we have already learned, that this part becomes 0, ln of 1 is equal to 0, so it remains ln of n minus 1 plus 1 here. But we have taken if the n is very greater than 1, That means n is very large value, so we can neglect this one here plus 1. So we can write it ln of n factorial is equal to n ln of n minus n. So this was a simple derivation or proof of Stirling's approximation. Please note here we have simply used the integration by parts here and do the same procedure and you will get this equation. And also do the homework what I have given you in the video regarding calculation of two approximations, following the first Stirling approximation, then better approximation also. Okay, thank you.